Okay, now we come to the question, do all infinite sets have cardinality all of null? It certainly is striking that the rational numbers, of which there are infinitely many between any two integers, have the same cardinality as the integers. There are infinitely many integers, and in between any two integers there are infinitely many rationals, but even if you take all the possible rationals, the cardinality still doesn't exceed that of the counting numbers. We can put counting numbers on the rationals in a systematic fashion that assures us that they can be numbered. So we come to the question, do all infinite sets have cardinality all if null? Okay, now let's let R the set of real numbers. That consists of all, it can be represented, and we'll think of it as all decimal numbers, repeating decimals, terminating, repeating decimals like 0.35, 35, 35, and so on, which turns out to always be a rational number, terminating like 0.3786, that's it. And non-repeating, non-terminating. Now it's harder to think of these, but it's easy to think of what they'd look like. It'd just be a set, an infinite sequence of decimal numbers that never stop and never repeat. Now those are called the irrational numbers. Pi and the square root of 2 can be shown to be irrational numbers. And it turns out that the cardinality of the irrational numbers is greater than the cardinality of the rational numbers or the counting numbers. And we're going to see an argument that shows that. So let's say, first of all, suppose that the cardinality of the real numbers equals all if null. Then what can we do? We can write down a one-to-one correspondence between R and the counting numbers 1, 2, 3, 4, 5, and so on. Okay? So let's say that we do that. Let's just say that there is a way and we do it. Okay, so we're going to say, okay, let's say 1 corresponds to the number 0.86539, and so on. Non-repeating, maybe non-terminating, doesn't matter. 2 corresponds to 0.341296. 3 corresponds to, and of course this goes on, 0.911374, and so on. 4 corresponds to 0.219354, and so on. I'm going to construct a new number. And I'm going to construct a number that can't be on this list. And if I can construct a real number that can't be on this list, then I've proved that you can't do this. You can't enumerate the things. Now I'm going to underline the first decimal under the first number, the second, the hundredths place under the second number, the thousandths place under this one, the fourth place under this one. And then I'm going to write down a new number which differs from each of these. Okay, where I've got an 8 here, I'm going to use something besides 8. Let's use 3 instead of 8. Instead of 4, I'm going to use 7. Instead of 1, I'm going to use 2. Instead of 3, let's use 8. And of course, this list continues so that this number is going to continue forever. Now, once this number is constructed, this number can't be on this list. Why? Well, it can't be the first number because the first number starts with has an 8 in the first in the 10th place, and this has a 3. It can't be the second number because this one has a 4 and this one where this one has a 7. Can't be the third number because this has a 1 where this has a 2. Can't be the fourth number, this one has a 3 and this one has an 8 in that place. Since I'm going to continue that pattern, this number is not going to be the same as any of these numbers. Okay? So, the new number wasn't listed, so the correspondence is invalid. That's going to be true no matter what correspondence you try to construct or write down. You can't write down a one-to-one correspondence between the real numbers and the counting numbers. Since you can't write down a correspondence, there is no correspondence. I mean, you can't, of course, you couldn't write the whole thing down, but there can exist no correspondence because whatever correspondence there was, you could do this and come up with a number that isn't on the list.